Okay, hello everyone. I just wanted to actually do this for you. These first few problems, we're just learning some examples that we will use from now on. So these problems are sort of heavy on the memorization, but they're just memorizing these examples that we were going to use again and again. So we become familiar with these, they're our friend, and they're going to come up everywhere. Like if I search Wikipedia, let's see, where's Wikipedia? For the light cone. The light cone is exactly one of these things we're going to see. This is in special relativity. And so let's go to GeoGebra, geogebra.org. I'm going to click the 3D graphics. And then I'm going to put x squared plus y squared minus z squared, that was the equation, equals s, and hopefully it'll create a slider for me for this variable s. Excellent. So at first s is equal to 1, and here we get this object. This is the preimage of 1 under the map that sends xyz to x squared plus y squared minus z squared. So it sends xyz to x squared, the number x squared plus y squared minus z squared. And then to look at the preimage of the point s, or the point 1, I make this equation, and then GeoGebra draws all the solutions to the equation. You can't type this into GeoGebra. Yeah, anyway, so I'm going to just press play. So here are the preimages. They're all connected when s is a positive number. Then, boop, they split apart. That's really, I like that. Now it's a disconnect. There's two pieces, a bottom half and a lower half. Then they come together and they form just one piece. And so these are the preimages of different numbers from the output space. Now, if I stop it and I go to 0, 0 is where everything changes. So here I get this cone. This is the light cone. This is sort of the future is in the top half of this cone. The past is in the bottom half of the cone. And the things that are out here, outside the cone, you can never interact with them. So this is something weird about special relativity. I highly recommend you look it up. It's pretty crazy. Okay, that was good for this example. What's the other ones? Oh yeah, this one. Let's look at this map. So the graph is sort of like what we can do by default. Let's take xy goes to x squared plus y squared minus 3. Let's do that. How do I do a new? Oh, delete. Okay, here we go. So let's turn off this equation and let's do x squared plus y squared minus 3. And so right away what it does is it gives a graph. So this is the graph of the map that sends xy to the number x squared plus y squared minus 3. So this third axis here, this blue axis, is the height. It's representing the output space. The input space is the red and green plane. Actually, this plane in gray is the input space. And when you put the input space and the output space together, you get the graph. These are all the points on the graph. Now, if we slice at different heights, we're going to get the contour plot. So notice that if I slice at minus 3, I just get a point. If I slice at minus 2, I get a small circle. If I slice at minus 1, at height minus 1 with a horizontal plane, I get a little bigger circle. If I slice at 0, I get a circle with radius square root of 3, which is like 1.7. It's a little less than 2. And so how can I see that? Well, let's go to GeoGebra, okay? And let's do it in 2D. X squared plus y squared minus 3. Now I want preimages of various points. So I'm going to create S, and it'll make a slider for me. Then I press play. So when S is big, I sort of get big circles. And then when S starts to decrease, It'll decrease, 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 decrease. It'll get smaller and smaller. And right there, I missed it. Now it's too small. And that's slicing below down here at like -4. We don't get any points. And so the slices are what you're seeing in the contour plot. Yeah, okay. And I highly recommend that you watch the video that is here. If you click on the problem list. Oh, no, not that one. Hold on. This one. See this video for nice. If you click on it, it should bring up this very nice video.
I have here
that explains
three-dimensional graph.
Sort of more things about contour plots and graphs. Especially this picture with slices, and then, so there's where the slices hit the graph, and then remove the graph, and then take just the slices and plot them
dimensional, and it still represents
there. And now we have a two-dimensional image that represents this map from 2D to 1D, from R2 to R1. So this is the contour plot, and this is the graph.